We are given the force vector, so we don't have to put the force in Cartesian component form. It's supplied to us that way. So that vector F is 300I minus 200J plus 150K newtons. And again, what we want to find is the moment about the axis AO, or in this case, OA. There is actually a difference. It starts at O and points towards A. So the OA axis and the AO axis lie on top of each other, but the direction of it will make a difference. So we want to find the moment as a vector around the OA axis. So it's not just the magnitude that would not have a bar over it, but I want the vector form of the moment around the OA axis due to, in this case, a single force F. So when I make my diagram for this, I'm going to copy pretty much all the information I have and put also the coordinates down, since that will be helpful down the road a little bit. Right, so the pipe goes 0.3 in the x direction, and then turns towards the y direction, and then turns to the z direction. So what I want is the moment around this axis that goes from O towards A, which means I need the coordinates of 2 points on that axis so that I can find its unit vector. O is at the origin, so A, I can put its coordinates down. So to get to A from the origin of my coordinate system, I have to go 0.3 in the x and 0.4 in the y, and 0 in the k. I'm going to need the coordinates of point B, because when I take the, when I want to find the moment around a point, since the force F is acting at B, I'm going to need to know some position vector that's going to terminate at point B. So I also want point B's coordinates will be 0.3, 0.4, and then that's going to be 0.2 below in the negative z direction. Oops. So negative 0.2. And the vector F, they supplied us the components of it. I don't have to rewrite it here. If I wrote it here, it's going to get a little bit cluttered if I do that. Right, for this problem, let's start at the end and work our way forward so we know where we want to get to. Remember, what we're asked to find is the moment around axis OA. Right, I need this thing's magnitude first. And then what am I going to multiply that with? Right, so from that previous slide, if I know the magnitude of the moment around OA, I can multiply it by the direction of OA to get this. Right, so we know how to find a unit vector. We don't know it currently, but we know how to find that. Before we do that, we need to find the magnitude of the moment around OA. So also let's put a plan of how we find that. One option would be if I know the moment around O, I can dot that with the direction OA. Or, if I know the moment around A, I can dot that with U hat OA. Or if there any point that lies on this, if there was some point B that for some reason was convenient, if I knew the moment about B, I could also dot that with O, with the unit vector OA. So any point that lies on that axis, I can find the moment about that point. Since the origin lies on this axis, probably this is going to just be easier to find by hand. But we can also use the moment around A, and that would be all right also. So going one more step, we know if we find the unit vector up here, we know it down here. Right, we want to use the cross product. So there's only one force in our problem. So what will the moment around point O be mathematically? Right, R will be cross F. Right, so this is what we looked at Wednesday. The moment around the point was the position vector that started at the point where we wanted to take the moment about. That's point O for this case. And force F is being applied at B. So this position vector goes from O towards B and then gets crossed with F. All right, so to solve it, we're going to go kind of backwards here. So we know where we want it to end up. So we know the pieces that we're going to need. We're going to need to take a cross product. We're going to need to take a dot product. This, once we have this, we'll put it into here. Once we have that, we put it into here. So that'll be kind of our plan going forward. So let's start with find the moment around a point that lies on that axis. In this case, let's start with MO. So we only have to do a single cross product for this one. We were given F in component form, so I can fill out that third row. So I need to find what position vector OB is. So it's going to be the endpoint minus the start point. Again, I chose this because it's a little bit more convenient to use the origin, just because the start point is always 0, 0, 0. But regardless, it's endpoint minus start point. My endpoint is B. My start point is 0, 0, 0, 0, 0. So the endpoint will be 0.3 minus 0 is 0.3. 0.4 minus 0 is 0.4. Negative 0.2 minus 0 is 0.2. Right, so this is my ROB cross F. This will give me the moment caused by F around point O, which is the origin. We spent Wednesday looking at this, so I won't go through the details of that, but we have this 3x3 determinant, and we can find the moment around point O as a vector. The cross product gives us out a vector quantity. So if we actually go through and do this cross product, we get that the moment around point O caused by force F is going to be 20I minus 105J minus 180K. And that's in Newton times meters. So this step is exactly what we did Wednesday, finding the moment around a point. Now we did this because it's going to lead us to the moment about the axis, because now working our way back up, we can find the magnitude of the moment around the axis if we know the moment around any point on that axis, which now we just found, and then we dot it with the direction of that axis. And this is where some of the confusion sets in. Here I had to use ROB to find the moment, but to find the moment about an axis, I'm dotting it with, this is U hat OA. These are not the same, not based on the same position vector. This will be based on the position vector from O to A. So this I just found, I now have to find U hat OA to do my next step. How do I find the unit vector that points from O towards A? What's that?
The origin minus the A.
Opposite is true. So it's endpoint of A minus the origin O, or the start point O. So to find any unit vector, I can take the position vector divided by its own magnitude. So this is exactly what we've been doing before. The position vector OA is going to be the endpoint minus the start point. In this case, 0.3 I plus 0.4 J over the magnitude of that, which will be 0.5, since this is a 3, 4, 5 triangle. So the direction that points from O towards A, 3/5 I plus 4/5 J. We now know the unit vector that points from O to A. From the previous step, we know the moment around point O. So now we can go and do this dot product, which again goes back to what we did in section 2. So this is going to be 20I minus 105J minus 180K dotted with 3/5 I plus 4/5 J. We did the cross product. Now we have to do a dot product. They're different operations. So remember, for the dot product operation, we're going to multiply the like coefficients and then add it together and get a scalar result. So this is going to be 20 times 3/5 plus negative 105 times 4/5. Okay, so these are both i's, these are both j's, plus negative 180 times, in this case, 0, because this does not have a k component. Notice, again, there's no i's or j's in this line. These are just scalar values. So if I add 3/5 of 20 minus 4/5 of 105, I get this has a magnitude of negative 72 Newton meters. So now we're at the last step. We now have the moment, the magnitude of the moment around axis OA. So now we take that result and we multiply that scalar times that unit vector that we found before. So finally, the moment as a vector will be negative 72 times 3/5 I plus 4/5 j. Like we did in section 2, I can distribute that scalar value into my unit vector here. So I'm going to get negative 72 times 3/5 is negative 43.2 I minus 72 times 4/5, 57.6 j. Also in Newton meters.